We are now on to the last section of material. That went by very quickly, and this is kind of the mixture of various exercise physiology topics. We have thermoregulation that we're doing today, altitude, pregnancy, and then ergogenic aids. And remember that the final is cumulative, so it's based on the entire semester. And it includes these 4 lectures, obviously. So let me know if you have any questions in preparation for the final, but hopefully you guys do okay. So with thermoregulation today, just warning you, I have some odd pictures. It was hard to find thermoregulation-based pictures that weren't a little creepy and weird. So if they freak you out, it'll just bring you some entertainment for this lecture. For this lecture, we will be talking about heat loss versus heat gain processes, and you should be able to explain what determines if we will gain or lose heat and how each of these processes work. We will be discussing cardiovascular drift, and you should be able to answer what is it and why does it occur, and then we will be discussing heat acclimation and a little bit of cold acclimation. First, we are homeotherms. As humans, we are homeotherms, which means that we try to maintain a constant core body temperature always. And this is really important for our metabolic pathways, because if we get too hot, then we are going to destroy our proteins, and if we denature our proteins, that's bad because enzymes are proteins, and our enzymes make our metabolism run. So if we're too hot, we're destroying the enzyme, and therefore we are going to be affecting our metabolic pathways, and we will not be producing any ATP. But if we're too cold, then our metabolism will be going much slower because enzymes are affected by temperature, and so if it's going too slow, metabolism won't be going fast enough and we won't be producing adequate ATP. Our body will shut down a little bit. So as humans, we try to maintain a constant core temperature of about 37 degrees Celsius, which is about 98 degrees Fahrenheit. And if you think about when you have a fever, we consider a fever being just 100 degrees Fahrenheit. So only 2 degrees above what our constant core body temperature of 98 degrees is, we consider that dangerous to our body. So you can see that our body is very concerned with keeping this constant core temperature of about 37 degrees Celsius or 98 degrees Fahrenheit. So it's all about making sure that our heat loss is equal to our heat gain. And exercise is a big thermoregulation challenge because with exercise, we are producing a lot of heat. We talked about this in the first section of material. When we break down an ATP molecule, which we're doing a lot while we're exercising, we are allowing a muscle contraction to occur, and that produces movement. But when we break bonds, we release heat. So every time we're breaking down an ATP molecule and causing muscle contraction, we're producing a little bit of heat. And because we want to maintain a constant core body temperature, we need to make sure that we have adequate heat loss processes in order to combat this great heat gain that is being produced from the ATP breakdown. So what happens if our core temperature, what happens to our core temperature if we are losing a lot of heat and it's greater than our heat gain? If heat loss is greater than heat gain, then our core body temperature is going to decrease. And vice versa, if our heat loss is less than our heat gain, then our body temperature is going to increase. And so our body has to make sure that it has adequate balance of these, because we don't want a large increase in core body temperature or a large decrease in core body temperature. We need to keep it at that constant 37 degrees Celsius. Let's first talk about different ways that we can produce heat. So we are always producing heat. Even when you are sleeping, you are producing a little bit of heat, but when you're exercising, since you're breaking down more ATP, you are producing a lot more heat. And our bodies are only about 20 to 30% efficient. When we break down an ATP molecule, we really only get about 20 to 30% of that ATP molecule used for movement, and the other 70 to 80% is let off as heat. So we are very, very not good at utilizing our energy efficiently. So we're losing about 70 to 80% of our energy as heat, and therefore we have a lot of heat production while we're exercising. And we have two different classifications of our heat production pathways. We have voluntary and involuntary heat production. Voluntary heat production is like exercise. So we are voluntarily increasing our heat production by causing lots of muscle contractions. Involuntary heat production are things like shivering or when we're releasing hormones. So if we have a lot of shivering, that's not a voluntary response that our body has. We don't tell ourselves to start shivering, and shivering is just repeated muscle contractions. Our body responds to a lower core body temperature by causing a lot of heat contraction or muscle contraction, which is going to cause us to shiver. So if we have our max shivering, we're increasing our heat production by about 5 times our normal metabolic rate. So shivering is very helpful in increasing our heat production. Another involuntary heat production process is by releasing hormones. So we release catecholamines, norepinephrine, and epinephrine, and this is going to increase our metabolic rate. So we are going to go through metabolism a little bit faster, and that way we're going to be producing a little bit more heat. For this lecture, we're going to focus on our heat loss processes because when we are exercising, we are producing a lot of heat through our voluntary heat gain processes, heat production pathways of muscle contractions causing heat production. And so we need to combat that by promoting a lot of heat loss so that our core body temperature doesn't increase too much. And the 4 ways that we can cause heat loss to occur is through radiation, conduction, convection, and evaporation. These first 3, radiation, conduction, and convection, all work through a temperature gradient. So these 3 require a temperature gradient. Everything moves from a high to a low temperature. We've talked a lot about that with pressure, with air movement. So same thing here. In order for us to have heat loss, our body temperature has to be higher than the air or whatever we're touching, depending on which of these heat loss processes we're talking about. So these 3 require a temperature gradient. Evaporation doesn't require a temperature gradient. It actually requires a water vapor gradient, but we're going to get to that later on. The first heat loss process we're going to discuss is radiation. And radiation works by losing heat in the form of infrared rays. So we are transferring heat from one object to another without any physical contact occurring. So because our body is constantly producing heat, even when we're at rest, we're producing a little bit of heat, and if our body temperature is greater than the air temperature, then we are going to let off some heat via radiation through these infrared rays. Another example of radiation is how the sun sends infrared rays to the earth and heats up the earth via radiation. So I talked about how the first 3 heat loss processes work through a temperature gradient. So this means that all 3 of those can go either way. So if the atmosphere is a lot warmer than my core body temperature, then I'm actually going to take in heat because temperature is going to go from a high to a low temperature. So if it's 150 degrees outside, then my body is not it's lower than 150 degrees Fahrenheit, so I'm actually going to take in some heat. I'm not going to lose any heat. So you have to be careful about this. If you are exercising in a really hot environment, then you might actually be gaining heat rather than losing heat. The second heat loss process is conduction. Here's one of the creepy pictures. So conduction is when you have a heat transfer due to physical contact. So here we have a little baby who is laying on a metal table, and because the baby is warmer than the metal table, heat is moving from the baby to the table because it's moving down its temperature gradient due to physical contact. Then we have convection, and convection is when we have heat transfer through air or water molecules in contact with our body. So here's an example of air, and this example has a hot egg. I don't know why they chose a hot egg, but if something is hot, you can pretend that this is your face. If you just went running and you're really hot, and you put a fan in front of your face, wind is going to be blowing across your skin, and that those air molecules are going to cause heat to be lost from your face. Then if we look at water, so here if you are swimming in really cold water, then you are going to lose heat because of the water molecules in contact with your skin. However, if the water is warmer than your body, then again, the temperature gradient is switched. So if my body is warmer than the water, then I'm going to lose heat to the water. However, if the water is warmer than my body, then I'm actually going to gain heat from the water. It's not too often that water is warmer than your body, though. The three heat loss processes we just talked about, radiation, conduction, and convection, all depend on a temperature gradient. So it all depends on heat moving from a high to a lower temperature. However, evaporation does not depend on a temperature gradient. With evaporation, this is when we have a heat transfer from the body to the water on the skin surface, so sweat. In this picture, we have the skin surface, and the sweat glands are producing sweat molecules, or water molecules, and that goes onto our skin surface. And when those water molecules get hot enough, they're going to be converted into water vapor. And when that water evaporates and becomes water vapor, then it takes a little bit of heat with it away from our skin surface. And if we sweat more, that means we're going to be promoting heat loss. However, in order to have evaporation, evaporation is a heat loss process, the sweat actually has to evaporate. So any sweat that just drips off your face onto the ground is not helping with your heat loss processes. All it's doing is taking water from your skin surface produced by the sweat gland onto the ground. In order for heat to actually be removed from your body, the water molecule has to evaporate. Evaporation makes up about 25% of our total body's heat loss at rest, and radiation is actually our main form of heat loss at rest, takes up about 60% for radiation. However, during exercise, evaporation becomes the main player of our heat loss, and it is up to about 80% of our main heat loss process during exercise. Evaporation is dependent on a few different things. First is ambient conditions. Ambient conditions mean the air temperature or the relative humidity. So the higher the humidity, which means how much water vapor is in the air, then there's going to be less of a gradient for the water to evaporate from our skin into the air. Therefore, we're going to have less heat loss. Second factor is convective currents. So we just talked about convection. If we have a lot of wind or if we're in the water, then that's going to affect our evaporation. If there is a lot of wind that's just taking the sweat off of your skin and not letting it actually evaporate, then we're not going to have as high of a level of evaporation. If we're in the water and if we produce a little bit of sweat, but then the water just takes that sweat away from our skin, again, we're going to have less evaporation occurring. It also depends on the amount of skin exposed. So if you are wearing long pants and a long sleeve shirt, then you have very little skin exposed, and any sweat that is produced on your body is just going to be soaked up by those clothes, and you're going to have very little evaporation occurring. But if you wear a tank top and shorts, then you have a lot of skin exposure, and that's going to allow for much more evaporation to occur. Let's talk about those ambient conditions a little bit more with the humidity, because I think humidity is a little bit more of a confusing topic. Humidity is how much water vapor there is in the air. So on the left here, if we have 95% relative humidity in the air, that means we have a lot of water molecules in the air. On the right, if it's only 10% relative humidity, that means we have very few water molecules in the air. So you can see that on the left side, if there's a very high humidity and there's a lot of water molecules in the air, then our evaporation heat loss process is not going to be as efficient as if there is a low relative humidity, because evaporation works through a water vapor pressure difference. In order for evaporation to occur, the water vapor on the skin has to be greater than the water vapor pressure in the air. So here, if we have 95% relative humidity and we have a lot of water molecules in the air and we have a lot of water molecules on my skin, there's not as large of a gradient, so we're not going to be able to lose as much heat. However, if we have a low relative humidity, so there's not very much water vapor in the air, then there's a large gradient, and that water vapor on my skin wants to evaporate and go into the air. Here's a different way to look at it. We have temperature on the x-axis and relative humidity in percent on the y-axis over here. And on the right side, we have this is evaporation rate on the other side of the y-axis. So as you can see, as temperature increases, our relative humidity decreases. So we have less water vapor in the air, and that's going to promote our evaporation rate to increase. So the higher the temperature, that means we have less water vapor in the air, and therefore we are able to utilize evaporation as our heat loss process more. Now let's put all four of those heat loss processes together. If we are running in the sun, and so we're having muscle contraction, which means we are producing a lot of heat, we can lose some heat through radiation. So infrared rays, just because my body is producing more heat, the temperature gradient is going to allow us to lose heat, not through physical contact, just to the air if the atmosphere is a lower temperature than my body. We also have some evaporation occurring from me sweating. And we also have a little bit of evaporation occurring because when we exhale, we are losing a little bit of water. Every time you exhale, you lose a little bit of water. And that takes a small amount of heat away from your body. It's a very, very small amount, but it does help with evaporation and heat loss a little bit. Down here we have conduction, which is the heat loss due to physical contact. So if you're touching the ground and the ground is less hot than your body, we will lose heat. And you can think about if you're doing an activity that requires physical touch to many different things, like biking. So you have the bike seat, you have the handlebars. You're going to have a lot more conduction occurring with those kind of activities rather than running. Then we also have convection, and convection is through the heat transfer through air or water molecules, so the wind going across a person's face as they are running. How can we have optimal heat loss during exercise? We just talked about how we can lose heat, but if you know that you're going to be exercising on a hot day, or if you are looking at the weather and you're deciding which day you should run outside, if there's a hot day versus a cool day, which one is going to promote optimal heat loss? So radiation can be affected by if you wear less clothing. So if you wear less clothing, then you're going to have more skin exposed to the atmosphere, so you can have more radiation occurring, and more heat is going to be able to leave your skin to the atmosphere if the atmosphere is a lower temperature than your body. You can improve your conduction by, if you're doing a sport that requires lots of touching of a ball or a bat or something, then you want to make sure that those objects are cold. So some people, if in really extreme circumstances, they'll put maybe bats in ice or gloves in ice. Then that is going to improve your conduction heat loss. You can also put things like towels, cold towels on your body, and that's going to help with heat loss if the temperature is colder on the towel compared to your body. With convection, if you're exercising on a cool day that is windy, that's going to allow more air molecules to move more heat away from your body, or if you want to exercise in a colder pool. Then finally, we have evaporation. So again, less clothing is going to help with a higher evaporation rate. And also if you're exercising in a lower humidity day. That way there's a larger water vapor gradient in between your skin and the environment. How does our body regulate our temperature? It's mainly through our hypothalamus, and our hypothalamus is in your brain. And so if it's really hot outside, then our core thermoreceptors are going to sense that our core body temperature is increasing. And the skin thermoreceptors are also going to sense an increase in body temperature. And when our core and skin thermoreceptors sense this increase in heat, it's going to send a signal to the hypothalamus in our brain. And the hypothalamus is going to respond by increasing our sweat production. If we're sweating more, then we're going to be increasing our evaporative heat loss process. The hypothalamus is also going to send a signal to vasodilate our blood vessels feeding our skin. And if we're vasodilating our blood vessels feeding the skin, that means we are losing more heat from blood being taken away from our core and out to our skin, and that's going to allow a larger gradient to occur for radiation or conduction or convection, because the skin temperature is going to be higher, and since those allow heat to be lost through a temperature gradient, if there's a larger gradient in between our body and the environment, then we're going to lose more heat. What about if we are exercising in the cold, or if it's just cold outside? If it's cold outside, again, our skin thermoreceptors are going to sense that it's cold, and our core thermoreceptors are going to sense if our core is getting lower. Again, they're going to send a signal to our hypothalamus, And it's going to cause vasoconstriction to our skin to occur. So now we will have less blood moving to our skin, and more of it will be kept at our core, and that's going to help us increase our core body temperature. We're also going to start shivering, and this was our involuntary heat gain process. So if we start shivering, then we are having much more muscle contraction, and that's going to increase our heat production. And finally, we're going to increase our hormone release. If we are releasing more hormones like epinephrine, and norepinephrine, then we're increasing our metabolic rate, and we're going to increase our heat production. Now let's talk about our body's responses to exercising in the heat. So with core temperature, we have core temperature on the y-axis here and exercise time on the x-axis. So this is at a constant steady state intensity. If we are exercising in a cool environment, our core temperature is still going to increase. It goes from about 37 degrees Celsius almost to 38 degrees Celsius, and then it's going to plateau off. We're at a steady state intensity and we're in a cool environment. If we're exercising in a really hot or humid environment, then our core body temperature pretty much continuously increases as we are exercising, because we're having a harder time losing heat from our body as we are producing it, since the environment is hotter or more humid, so we can't utilize our heat loss processes as well in comparison to the cool environments. If we look at core temperature with increasing exercise intensity, so exercise intensity is on the x-axis, core temperature is on the y-axis, you can see we have a linear increase in core temperature. As we are exercising at higher intensities, our metabolic rate is increasing, so we will be producing more heat, which is going to increase our core body temperature. Sweat rate, so this is going to be our marker of our evaporative heat loss process. We have sweat rate on the y-axis and time on the x-axis, so again we're at a steady state constant exercise intensity. The blue line is a cool environment, and we're going to have a little bit of an increase in sweat rate as we are exercising. But if we are exercising in a really hot or really humid environment, then we're really going to increase our sweat rate, because we are having a harder time getting rid of our heat through the other three heat loss processes that depend on a temperature gradient. And so we're going to respond by increasing the amount of sweat we are producing so we can increase our evaporative heat loss. And if it's really humid out, then we're going to try to promote more sweat being produced on our skin so that hopefully we can take a little bit more heat away from our body, since we're not doing such a great job of actually evaporating that sweat off of our skin, because there is not as large of a water vapor pressure difference between the skin and the environment. So we're going to increase our sweat rate whether it's hot or humid. Now let's talk about this idea called the cardiovascular drift. So cardiovascular drift generally occurs mostly during endurance type activities in the heat. So you have to exercise for at least an hour to really see cardiovascular drift, and so it's an endurance type activity. You're not going to see cardiovascular drift occur as much if you're doing sprinting type activities. And cardiovascular drift means that our cardiac output for a given intensity is maintained, but our stroke volume is decreasing and our heart rate is increasing. So you can see that here we have time on the x-axis, we're exercising at a constant intensity, and on the y-axis we have % of 20-minute value. So if we are going above this 100, that means that, so here we have heart rate. Heart rate is increasing above what the value was at 20 minutes. And if we are decreasing, here we have stroke volume, that means that stroke volume is decreasing compared to what it was at 20 minutes of exercise. So with cardiovascular drift, our heart rate is increasing over time and our stroke volume is decreasing over time. And that's to help maintain our cardiac output. And you can see here that our cardiac output is decreasing over time, but not to the same extent that stroke volume is decreasing. If heart rate just stayed the same and stroke volume was decreasing, then cardiac output would decrease much more. It would look more similar to the stroke volume line. However, since heart rate is increasing, it's combating this decrease in stroke volume and helping maintain cardiac output a little more, so it doesn't have as large of a decrease. Why does cardiovascular drift occur? Why would heart rate increase and stroke volume decrease? Well, if we're exercising in the heat, then we are sweating a lot more. And if we are sweating a lot more, that means we are losing a lot more water, since sweat is water. If we are losing a lot more water from our body, that means our plasma volume is decreasing. If our plasma volume is decreasing, what is that going to affect? It's going to decrease our venous return. Remember, we talked about with endurance training, we have an increase in plasma volume. So that's going to allow us to increase our venous return back to the heart. If our plasma volume is decreasing because of our increase in water release due to sweat production, we're going to have a decrease in our venous return, and therefore we're going to have a decrease in our stroke volume. So because we are losing so much water due to sweating so much, we're decreasing our stroke volume, and that would cause our cardiac output to decrease at a given intensity. But we know that we need to maintain our cardiac output at a given intensity so that we have the appropriate oxygen delivery. So in response to this decrease in stroke volume, heart rate has to increase so that cardiac output can be maintained. What's going to happen once we reach our heart rate max? Let's say we're exercising for so long that eventually our heart rate increases all the way up to our heart rate max of 220 minus our age. So heart rate max has been reached, but we're not going to stop sweating and we're not going to stop losing water. So stroke volume is going to continually decrease. Over time, if you're exercising long enough in the heat, your heart rate will stop increasing, but your stroke volume will continue to decrease. So then what's going to happen to cardiac output? It's going to decrease. Eventually, you will have a decrease in cardiac output and a decrease in athletic performance. This is why it's really important to keep hydrated while you're exercising in the heat so that you don't have this decrease in stroke volume and cardiac output. Let's talk a little bit more about heat and your athletic performance while exercising in the heat. If you are exercising in the heat, you're going to have an increase in your glycogen depletion. If you are depleting more of your glycogen stores, that means you're going to have an increase in your muscle fatigue. Your body becomes more fatigued the less carbohydrates you feed it. So you're not going to have as high of an athletic performance as you continue to exercise in the heat due to glycogen depletion. You also produce more lactate in the heat. And this, if you have an increase in lactate production, this increases your muscle fatigue, and it's going to decrease your metabolic activity. It's going to decrease your ability to utilize glycolysis. So you're going to decrease your ability to produce ATP. You're also going to decrease your muscle blood flow, and this occurs only at really high intensity exercise. If you're exercising at a low or moderate intensity, then your muscle blood flow isn't really affected. This only occurs at high intensities. So your muscle blood flow will decrease if you're exercising at a high intensity in the heat, because where's that blood flow going? It's going to our skin so that we can increase our heat loss. We're vasodilating our arteries feeding the skin, and that's going to increase the blood flow going to the skin. However, it decreases our muscle blood flow, and therefore we're going to have a decrease in our athletic performance since we're not delivering the appropriate amount of oxygen. How is this going to affect our VO2 max? Well, we just talked about how if we exercise in the heat, we're decreasing our stroke volume, and we're having a lot of water loss, so we're going to decrease our stroke volume. Our heart rate is going to be increasing a little bit, and our AVO2 difference isn't affected if we're exercising in the heat. So if stroke volume is decreasing, heart rate is increasing, AVO2 difference is not changing, then what's going to happen to VO2 max? VO2 max decreases in the heat because we have such a large decrease in our stroke volume. And we can see how much our hydration level, and therefore stroke volume, really affects our athletic performance. So on the x-axis we have distance, different distances of races, and on the y-axis we have running velocity, how fast they're running. The blue line shows someone when they're hydrated, and the red line shows when they are dehydrated. If we look at this person's athletic performance, their running velocity, when they ran a 1.5 kilometer race, you can see that they decreased their running velocity by about 3.1%. And then if we go to a longer race, so now we're running a 5K, when they're dehydrated, they have decreased their running velocity by about 6.7% in comparison to when they were hydrated. And then if we increase the distance even more, now we're running a 10K. Again, this person is running at a slower speed when they are dehydrated compared to hydrated. So they decreased by about 6.3%. So you need to really make sure that you stay hydrated in the heat, because if you are dehydrated, you can't perform as well due to your decrease in stroke volume. Now let's discuss heat acclimation. Heat acclimation is when you have an improved tolerance to a heat stress following repeated exposure to the heat. So you can become heat acclimated naturally by moving somewhere that's really hot. So if you move to Arizona, you can also do it in the lab if a lab has a heat chamber. And so I did a heat acclimation study at my old school, and we had to make my subjects had to walk in a heat chamber, which was about 105 degrees Fahrenheit for an hour and a half for 8 days in a row, and then we consider them heat acclimated. So you can do it in the lab or just naturally by moving somewhere that is really hot. And you can see that as we have 14 days of heat acclimation, on the x-axis we have 14 days of heat acclimation, and then on the y-axis we have how do these different variables change from their first day of trying to become heat acclimated. So we're going pre to post heat acclimation. You can see in the blue line that plasma volume increases up until about a week and then plateaus off. And based on what we just discussed, you should be able to explain why an increase in plasma volume would be beneficial to exercising in the heat, and then also explain why this red line, which is heart rate, would decrease for about a week and then plateau off. It all has to do with cardiac output. You see in the black in this light green line that our skin and core temperature decrease, so we are better prepared for having an increase in our core body temperature by exercising in the heat. And our sweating rate in this gray color, we start sweating a lot more. When you become heat acclimated, you sweat sooner and you sweat more, and that's going to improve your heat loss process. And then finally, we have your exercise capacity in this light blue line. So your exercise capacity is going to increase in the heat as you become more heat acclimated. So you are better at performing in the heat after you've become heat acclimated. This doesn't mean that you're better at performing in a neutral temperature environment, but you are better at exercising in the heat. We're going to talk about some of those factors a little bit more. So with plasma volume, if we are looking at someone's plasma volume as they become heat acclimated for 22 days, on day 1, so pre-acclimation, they have a pretty low plasma volume, and then it's going to increase for about a week, and it stays pretty constant for the rest of the time that you are becoming heat acclimated. So up until this person was being acclimated for 22 days. So again, you should be able to explain why an increase in plasma volume would be beneficial to stroke volume and cardiac output. Heart rate decreases as we become heat acclimated. And heart rate is going to decrease due to an increase in our plasma volume. Because if we have an increase in plasma volume, we're increasing our stroke volume, and therefore we can decrease our heart rate in order to maintain that cardiac output. Our sweat rate, these black lines represent post-heat acclimation, and these white circles represent pre-acclimation. You can see that when you are heat acclimated, you sweat a lot more, and you also sweat earlier. So this person is sweating much more at minute 5, and they reached their peak sooner compared to this pre-acclimation person who reaches their peak later, right here, closer after minute 5. So post-acclimation, you sweat more and you sweat sooner. Now we're going to discuss cold acclimation. We don't have as many studies looking at cold acclimation because there aren't as many events that are done in the cold for extreme long distance races. Most of them are done more in neutral environments or the heat, and people are just less willing to do cold acclimation studies compared to heat acclimation studies. So we have less information about cold acclimation. But body fat is insulating. So based on this, would men or women be better at handling the cold? Women would be, because they have more body fat. So they are better at insulating their heat, and they're not going to lose as much heat to the really cold environment. Because while we are exercising, yes, we are producing more heat. However, if we're exercising in a really cold environment, we don't want to lose too much heat from our body, or our core body temperature will decrease, and we can't have large variations in our core body temperature. If we become cold acclimated, we decrease the skin temperature to start shivering. So you will start shivering sooner if you are cold acclimated. And that's beneficial because you are going to be producing more heat through shivering, and you're going to help increase your core body temperature. So this isn't going to necessarily happen while you're exercising, but if you become cold acclimated and then you just live or you visit a cold area, then you're going to start shivering sooner. You're also going to increase your hand and foot temperature. So this means that you have improved vasodilation to your hands and feet. And since these have very small arteries and they can easily they can easily lose all of their blood flow to them because they have a lot of heat loss. If we have a lot of blood flow to our skin, to our hands and foot, then our body is better at vasodilating these arteries to our hands and feet, and that's going to increase the temperature at our hands and feet so that we're less likely to get things like frostbite. That was thermoregulation. If you have any questions, please let me know. Quiz 6 is on Tuesday, June 28th, and that's supposed to be on. It's on thermoregulation and altitude. So this lecture and the next lecture. Let me know if you have any questions.